This session is about linked list. We'll start by structures and move on single linked list, then doubled linked list. Before we start typing code for linked list, we need to first understand um, the concepts about structures, why we need structures for linked list or double linked list. Or maybe in other situation, we might need structures. So they are very important for all the coming things. So let's start by including the libraries like the S3 IO library and the S3 lib library. Then define the main function. We don't intend to receive any argument, and the function will return 0. Great. So now let's say we want to represent something like a um, let's say we have names of peoples and their age. Let's say a student. So I'm going to define a struct named student. The fields are the name field, so we can save name in the struct, and also the age field. Then we're going to define a type, the type def struct student. The type name would be student type. Or let's make it simple. I'm just going to type in the type def keyword here, type def. Then we define the type student type. So this is a struct. A struct is, we can say, a composite data type where you can have multiple other data type gathered under the same name. And when you define a variable of that type, a memory space will be allocated to hold enough space. For now, I'm just going to add, I'm going to say the name field would have a length of 20 character or 30 character. So let's define a variable that that represent a student. So a student type S1. Then we have another student S2. So these are student variables, and we can even declare an array of student. For example, I can say students, so an array of 10 students. The same as when you define an array of integers. For example, an array of numbers, 10 numbers. So the same goes with the custom data types, like the struct we define here. So structs are useful when you want to, uh, when you have some real world things to represent. And these kind of data types, they are also, let's say, useful for other tasks. So we have a struct here, and I'm going to define an array of students. So this is a student type. Then I'm going to open another file named notes.txt where we're going to explain some of the things. So what happens when you define an array like that? So as usual, we'd have memory locations reserved for this array. So we'll have 10 memory locations for this array, and each memory location would have an address and a data it can store. So the data type in our case is of type student. Now, the size of this memory location would be the size of this struct. For example, you can add up the size of this array of 30 char character, and you can also add the size of this age variable. So the size of the struct is the size, the added size for each individual field in the struct. So we'd have memory locations for this array we just defined. And let's represent it like that. So we have 6 here. I'm going to copy and paste 1. Then we have 10 elements in the array. Per definition, an array is a collection of allocated memories locations. And these memory locations are kind of contiguous. So there are from one memory location to another memory location, you just need to add 1 or increment. So this is uh, what we have here. So for an array, all the memory locations allocated are contiguous, and we knows that from the beginning of the program, we knows that we need 10 students. What if you don't know the number of students you might need in your program? This is where we might need to find other ways to store our data and request memory locations when needed. For example, uh, maybe let's say if you want to allocate for 1,000 students, then you'd have 1,000 students allocated from the start of your program. And all these allocated memory location has to be contiguous in order for it to work. What if there is not enough space on your computer memory to save, to store these contiguous memory locations? So your program may crash. One idea would be to allocate only when you need it, and they don't have to be contiguous. We just need to hold an address for any allocation. So let's keep things simple. I'm just going to delete all these again and start over. And first, let's start with an array of integer before we move on linked list. So when you have an array, let's say we have numbers of 5 elements. So we have this array and the elements, the data are stored in the memory locations. So what if you want to represent this in like list, represent it in the list manner? So the data are integers. So the first thing I'm going to define is I'm going to say data item. And the data item store a value. The value is an integer data type. So that's one. Now let's add another field named next sibling. Next sibling. I hope there is no typo here, or let's just say next because it's more simple. Next. And the type of this field would be a struct type. So it is a pointer. It is a field that can store an address for a struct data item type. And I'm going to define a type define, and we have this thing called data item type. Now, the advantage with this thing is that you can create a data item, then create other data item, then each data item can hold a reference to the next data item. So you can jump from one memory location to another memory locations once you know the first allocated element. For example, let's define a variable called data item. It is a data item type. This will be the first data item we're going to allocate. I'm going to say malloc size of data item type. Now what happens, a memory location is created and the address is returned and saved inside these variables first. So we can create any questions. Then we can create a data item, a second data item called, let's say, second, and create allocated memory for that. So size of data item type. Then we can create a third one, size of data item type. Now I'm going to set the value for each of these data item elements we just created. So for the first one, we can say first value equal 1. The second, the value is equal to 3. And the third, we're going to say the value is equal to 3. Oh, for the second, I'm going to say 2. And the third, the value is equal to 3. So what I can do is display these data items like that. So printf, for the first one, we're going to display first value, and the second will display second value, and the third we will be displaying third value. Then let's run this program. I'm going to compile the code and run the program. In the terminal, you can see that we have 1, 2, 3. For now, these data items, they don't hold reference to each other. For example, you cannot, when you know the first data item, you don't have a reference on the second one, and you also don't have a reference on the third one. So what we can do, for example, we can say the first data item will store a reference or the address of the next of the second one, and the second data item will store a reference to the third data item, but the third data item don't have any reference. So we're going to set the next element to null. So that way,
Excuse me, Mohammed.
yes,
I wanted to ask something.
yes.
When you declared the first and second and third data item, why did you use pointers to allocate the size?
Yes, true. It's here when the malloc function will request memory location that has enough size to store a struct data item type. So we'll have on the right side, you can see. So we'll have a memory location, which will have an address and a data it can store. So once the malloc function return, it has to return the address of the memory location so we can change the data stored in it. So this is why we defined another variable that can store an address. An address
Okay,
for a memory location that can store a data item type data.
okay.
So the
Now I
start,
understand.
yes. So the star sign is to say that this variable can store addresses. It doesn't store the actual data, but the address for the data. Uh, so this is, I think, the way. So now we have the first data item that store the address for the second one, and the second data item store an address for the third one. The third one, there's no fourth data item, so we are going to say the next item will be set to null. Now, since the first element holds a reference for the second element, we can say that printf, we're going to replace this printf function by typing first, then the next is, the next item is element in the list, then we can say value. So if we want to access the third element, we can start from the first element. So the first element next item is the second item. Then the second item also has the next item. Then we can access the value for the third item. It can continue on and on and on as long as we have other items in the list. So we can start off from the start till the end of the list. Now, if you run this code, what you can see, we see 1, 2, 3. So we're just playing with memory addresses. So one data item store data item type store the address for the next data item. The other next data item store an address for the other next data item. So that's why we call it a linked list. They are linked. And if we notice, we see that there is only one way to go. There is no backward way. Once you go to the next item doesn't hold a reference to the previous item. And this is the principle behind this. And I'm going to change this code a bit. Let's say we have a fourth data item just to make the list a bit bigger. The fourth, a fifth, and the sixth. So this is fourth, fifth. I don't remember how to type that, or maybe sixth, fifth. So we created 6 data item in the memory, and the malloc function return the address of each of the memory locations. The reason why we need to store the addresses is because we're not in arrays. Arrays, the data items in the array, they are stored contiguously. So once you know the address of the first one, you can add up one to get the second one. But here, when you allocate memories like that, for each malloc allocation, the memory location may change may move somewhere else. So maybe if, for example, the first item may be stored in the memory location 1, and the second item may be stored in the memory location 100. So you cannot add 1 to 1 to get 100. This is the difference between linked list and arrays. So let's link all these data items because we know their memory addresses. So the first thing I'm gonna do is I'm gonna say the fourth data item value is 4. The fifth data item value is 5. And the sixth data item value is 6. Then the next thing, we can link those data items because we know their memory addresses. So the first data item will hold a reference or the memory address for the fourth one. And the fourth one will hold a reference for the sixth, the fifth one. And the fifth one will hold a reference to the sixth one. Now we can display, yes, I forgot. For the sixth one, this also can hold the reference. There's no seventh element, so this will hold the reference to nothing. We'll set the next item to null. So as usual, we have to start with the first element. Let's say, we can say first, then next, and next, and then next, then value. So as long as we know the address for the first element, we can jump from one memory location to another by using the references. Now this code is starting to get lengthy. So what I'm gonna do is to use a variable that can store the addresses, then we loop through the list. So I'm gonna define a variable called, I'm gonna define it like that. I'm gonna call it cursor. So a cursor, this cursor variable is a pointer because we have the star sign, which means it can store the addresses for memory locations. But what kind of memory location? It is a memory location that can store a data type of data item type. So instead of printing things like that, we can use a loop. I'm going to change that a bit. I'm going to say we're going to set the cursor to the first address. So we have the address of the first element. Now the next thing is we can say printf cursor value. Then we move the cursor to the next element. So we can say cursor next equal cursor next. Then we print the value of the current element. Sorry, I want to say value. So we're starting to see a pattern here. So we set the cursor to the next element, then we display the value of the current element. So the cursor will store the references one by one and display the values, which means we can use that in the loop. I'm going to delete all this code and say, while the cursor is different than null, we say cursor. We print the value stored in the cursor. So the cursor is on the current, it represents the current element. Then we set the cursor variable to the memory address of the next data item. So that way, this loop will check if cursor is different than null, because once the cursor hit on the sixth element, like here, the next item will be null. So when cursor next equal null, the loop will stop. Let's compile and run this code and see. I'm going to clear the terminal. So we have this result in the terminal, the output 1, 2, 3, 4, 5, 6. So with the cursor, we know the reference for the first element. So we don't want to lose the reference for the first element. Now, what I want to say is we don't need all these variables. It is for convenience, but we don't need all these in order to define or to have other data items. We can simply delete all this code and see what is possible. We have a first data item, then the first data item will hold a reference to the next data item like that. So we call the malloc function size of data item type. Then if we have a next data item, this next data item also can store a reference to another data item. So we call the malloc function size of data item type. And still, starting from the first data item, we still have to move to the next data item. And then the next data item will have a new element, size of data item. And the last one here, the third data item or the fourth data item will not have a next element. So we're gonna set the next to null. That also works. So what is important is that we still can malloc whenever we need a new data item and just attach it to this kind of list we have here. So we just have to make sure we don't lose the references. And in order to move from one reference to another, we need to define a cursor variable. So the cursor variable will be set to the first item, and that's it. So while the cursor is different than null, Then we're gonna say printf cursor value, then cursor equal cursor next. Someone had a question? Uh, so as we said, I'm going to rename the field. I'm going to rename the field value to something like data, because the struct acts like a container or for the data we want to store. The data can be anything. It could be an array, can be a string, can be whatever. But the principle is that we want to be able to access those data by jumping from one container, which is the struct, from one struct to another struct, knowing that each struct holds the data we might need to process. So someone asked a question. I think we are at a 40-minute limit on the Zoom. So I'm going to restart the session and we can connect back.